In this video, we're going to look at sound waves. We're going to cover the different types of waves, sound waves, and the transmission of sound waves. Waves are classed by the direction of movement in the particles. In a transverse wave, the particles move perpendicular to the direction of propagation. So what that means is that in this wave, for example, the wave is moving from left to right, and the particles are moving up and down. This could be in the other plane of movement as well. You could be looking at movement from left to right. And examples of waves that are transverse waves are electromagnetic radiation, as well as secondary seismic waves. The other type of wave is a longitudinal wave or a compression wave. And in a longitudinal wave, the particles move backwards and forwards in the direction of propagation. So you can see here that this wave is propagating from left to right. And if you look at the highlighted red particles, you can see that they are moving backwards and forwards, or from left to right. Examples of longitudinal waves are primary seismic waves, as well as sound waves. So as I said, sound waves are a compression wave or a longitudinal wave. They generally travel through the air, although they can travel through other mediums. And they have a frequency of 20 Hz to 20,000 Hz, which means that those compressions are occurring at between 20 times per second and 20,000 times per second. Now this is the hearing range for humans. Other animals can hear higher and lower, and it just depends on the way the structure of the ear is for those animals. So for example, dogs can hear much more, and as you get older, your ability to hear, especially in the high frequencies, decreases. So not all humans will be able to hear up to the 20,000 Hz. These sound waves are caused by vibrating objects, and it can be anything that's vibrating, the vocal cords, the speakers in your computer at the moment, the strings on a musical instrument, or the reeds, or just the air itself vibrating. And this causes compressions and rarefactions. So compression is where there are lots of molecules compressed together, and a rarefaction is where they're split apart. And then these compressions and rarefactions, these compression waves, are picked up by the ear and then transferred into what we hear as sound. So as I said before, that the sound waves are propagated, so are sent along the vibration of particles in the medium. So this means that the medium, and in particular how closely packed the particles are, is going to affect how efficiently the sound moves through that medium. Now we usually think of sound waves as going through the air because that's what's all around us. However, sound waves aren't very efficient at travelling through the air. And this is because the particles in a gas are quite spread out. So it's hard for one particle to vibrate and pass its energy on to the next particle. In liquids, and even more so in solids, because the particles are tightly, more densely packed, the sound travels faster and further. So in liquids, sound travels at about 4 or 5 times the speed that it does in air. And in a solid, for example steel, the sound travels at about 12 times. The inverse of sound traveling faster and further through materials that have tightly packed particles is that sound is unable to travel through a vacuum. This is because there aren't any particles in a vacuum, so therefore there's nothing to carry that energy from one place to another. And this is where the saying, "in space, no one can hear you scream," comes from.